Hello, this is Concrete Path and the final lecture for your RCC. That's a final lecture for the Prestress concrete beams. That we would say the topic is deflections of that Prestress concrete beams, deflections of Prestress concrete beams. Now we already know that if there is some beam and there is a dead load of that beam, there is dead load, live load, and we know that what is the deflection at the midspan, maximum delta maximum is that 5 by 384 omega L to the power 4 EI. And if there is point load at the midspan, I would say the deflection at the midspan is PL cubed by 48 EI. Now, because of the we want to say because of the pre-stress force P and its eccentricity, we want to say what is the deflections that can be developed because of that. So I would say that downward deflection, we're going to keep that as positive. Downward deflection because of the loads, that's positive. We are going to keep those values as positive. So this is your positive deflection downwards. And if I say, let's take the first simple case that you had this beam and cable is straight and the cable is at eccentricity, that's eccentricity of E below the neutral axis. So that means the moment that gets developed, that's actually hogging moment. That's hogging moment of P times E. Hogging moment of P times E. Can you draw the diagram for that? Can you draw the diagram, that bending moment diagram for that? Because of that moment P, because of that moment M. Can you draw the diagram? What should be the diagram for that? Because I would say the cable profile is straight, and correspondingly your moment would be also constant value of some moment P into E for all those sections along the length. You're having constant moment of P into E, and negative moment, that's hogging moment. So I would say your BMD would be negative P times E. Now if I say, can you draw the M by EI diagram? This is your M by EI diagram. And we had to use the concept of that moment area method. We are going to use the moment area method to calculate the deflections. Moment area method. So I would say you are kind of applying a moment that's hogging moment about the neutral axis. So this can be converted in this way, that this is some sort of beam is there, and you are applying some P force and also a moment of P into E at the ends, P into E, such that your deflection at the midspan is somewhat in this way. That's upward deflection is there because of this moment PE. So upward deflection is there. So I would say because of this, you can think of it in this way, that you had a simply support beam. You are applying some moment of PE at the ends, such that your deflection at the midspan is somewhat delta. And I want to calculate that delta based on the concept of moment area method. Now I would say, I know one point, that where the delta is maximum and theta is 0. So if I draw a tangent at that point C, I would say, what is this value? I would say this is the value deflection at point A with respect to tangent drawn from C, and that is equals to area, that's moment of area of M by EI diagram between those 2 points, A and C, about the point A. Similarly, we can say, what is the deflection because of this moment P. I would say that would be equals to that moment of area between the 2 points. Let's say this is at the midspan, this peak is at the midspan. So I would say your diagram area about the point A and C. Let's say this is point A, this was your beam ABC. So I would say this is the total area we have. Between the 2 points, and its centroid location, that is the moment about the point A. So that is actually L by 4. That's the centroid of that particular area is at a distance of L by 4. So the total deflection developed because of that. This is the area between the 2 points. What is the area between the 2 points? That is PE by EI into what you call as this length of L by 2. and moment of area, that's L by 4 times, that is the centroid of that about the point A. So that is the concept of moment area method. So this is PE L square by ATI, and this value is negative because moment is negative, so this value is upwards. That means the deflection is upwards. Deflection because of this moment is upwards. So your beam is going upwards because of that. But because of the dead load and live loads, beam is going downwards. So this is trying to balance the deflection caused by that external loads. Okay. Similarly, let's talk about the one more case. Let's talk about the one more case. That's the cable. That's bent cable. Cable is bent shape. If the cable is bent shape, let's say the cable is bent shape. There is some P force applied, and let's say that this value here, this is equals to E. And can you tell me what is the bending moment diagram developed because of this moment? I would say bending moment diagram is also same. If I cut any section, somewhere at the location of X, I would say at that location we are having some eccentricity of that P force about that section, some value of Ex, so such that moment developed at that section is equals to P into Ex about the neutral axis. So that is a linear function. I would say moment diagram is a linear function of that X. Similarly, that means your diagram would also be in this way as per the cable itself. So your diagram for the moment is also same as per the cable itself. So if I draw the M by EI diagram for this kind of cable, so your diagram would be also same with the maximum value equals to PE. So this is your maximum value of diagram, that's PE by EI, and that's negative hogging moment. Now I want to say, because of this, can you tell me what is the deflection? And it's similar to that of a simply support beam, and because of this P and E effect, it's having some deflection upwards. And I would say, what is this value? I want to draw tangent from C. I would say, what is this value? Delta A with respect delta 8C with respect to tangent drawn from C, and that means we have to calculate the centroid. Centroid we have to calculate with respect to point A. So that means centroid with respect to point A. If the centroid is here, I would say if the centroid of the area is here, I have to calculate it from the point A. So that's actually 2 by 3rd of L by 2. So I would say, what is the deflection? That is equals to deflection would be equals to moment of area, that's 2 by 3 of L by 2. This is the centroid of that area between the 2 points, and area of the triangle, area of that curve between the 2 points, area of M by EI diagram. That's 1 by 2 of PE by EI into that length of L by 2. So what is the total value we have? PE L square by 12 EI, yes. And this is also negative, that means it's upwards because the diagram is actually negative, so we have to take the negative value. So this is final value of negative PE L square by 2L EI. This is the effect of that bent cable. Third case is that if the cable is parabolic, if the cable is parabolic, let's say the cable is parabolic with eccentricity E0 at the ends and with some maximum value of E at the midspan equals to E. So I am applying that P force, and because of this one, similarly I would say the diagram developed would be also that in this way. This is your diagram, or we can say the diagram would be developed in this way. This is your M by EI diagram with a peak value of moment developed is at the midspan, that is PE, and divided by EI, that's your diagram, negative hogging moment diagram. Okay. And I had to say, what is the centroid? Where is the centroid? What is the location of that centroid? What is the distance of that from the point A? From the point A, I would say that's 5 by 8 of particular length, that's L by 2. This is the length of L by 2. So moment of area of this particular area between point A and C, between the end and at the midspan. So this is the equation for that. So your delta is equals to that's the location of centroid into area of that curve between the 2 points. 2 by 3 of L by 2 into P into E. That's negative, so this value is coming to be 5 by 3 6 are 3 2s are 6 into 8, 48. 5 by 48 PL square. Yeah, we have to see also that EI. We have to divide that EI also. PL square E by EI. That's your equation. Negative delta equals to P by 48 PL square E by EI. That's your equation. That's your equation. Now the case is there. Now the case is that if we are having eccentricity at the ends also, if you are having eccentricity at the ends also, let's take that case. Let's take that case also here. I would say this is neutral axis here. This is our neutral axis. We are having some E1, E2. Let's say this is our E1, and this part is E2. So we need to calculate for this one what is the deflection we have. And for this one, we write the equation. I would say this is converted into, see, I would say because for some part of the cable we are having that moment above the neutral axis. That is, for some part of the length we are having some sagging moment, and for some part that is below the neutral axis, some part it's having hogging moment. So to calculate that effect, we say we are having a cable, parabolic cable up to the length of L by 2, and this is all contributing negative moment, that is hogging moment. So it's all contributing negative moment. So we are having a cable for the length of L by 2 and having the maximum value of this what you call as sag, H equals to E1 plus E2, and this is all negative, contributing all that negative value. And there is one more cable such that extends in this way, such that we have a cable in this fashion up to this part, that's giving you a positive value, So we're also having a cable, that is such that the eccentricity from the neutral axis is constant value of E1, and that P force is applied somewhere here for the length of L by 2. So we have to calculate for these two that's value of that net deflection. I have the equation. I have derived the equation for the parabolic part. For the parabolic part, we have this equation. We have to replace here in terms of E. We have to replace here E1 plus E2, because this is now the function has become in terms of H. So all the part is same, all the data is same. Your delta would be negative 5 by 48 PL square E1 plus E2 divided by EI. And one more delta is there because of if the cable is straight. If the cable is straight, we have this equation. If the cable is straight, that is positive value of PEL square by 8 EI. PEL square by 8 EI. PEL square by 8 EI. And in this case, we have to use what is the value of E. In this case, we have to use that value of E that's above the neutral axis. It's above the neutral axis. That's positive sagging moment. So it causes M sagging, and this part causes M hogging. So its final net of these two would give you the effect as caused by this one, as caused by this cable, as caused by this cable. So actually the thing is that means once you try to calculate the delta because of this one, I would say you have to first calculate what is the delta caused by this part that's above the neutral axis. And one more is there after, once you reach it up to this point, after that the cable is below the neutral axis. It's causing hogging moment above the neutral axis. So we are having two different deltas. So how to simplify that? I would say we are having some effect such that that net value is, if I say this part, we are taking this part for the calculations, this part we are taking for the calculations, this part, then we subtract how much out of this part we are subtracting, then this part we are subtracting this part. So this part we are subtracting from the parabolic cable, such that in net value we are left with only this part. So that this part is already calculated. And after that, because we have kept the long parabolic part, so this part is also, this is not overlapped, so this part we can also calculate based on this sum of the two effects. Let me show it again. So we said these calculations can be solved in this way, that if you have this cable with some eccentricity E1 and E2 about the neutral axis, so this was E1 and this was E2, and we know that at the midspan we are having maximum deflection if this is L by 2. Okay, I would say I want deflection caused by because the eccentricity is above the neutral axis for this part, and I want that deflection caused for this part because the eccentricity is below the neutral axis. And for these two critical parts we have to calculate. I would say if I take a general that we have a cable such that that cable is throughout the length up to the L/2, that's having in this fashion. So it would calculate the deflection for the entire part, for this entire part. Okay, it would calculate all the deflection for this entire part. But I don't know, I don't need it, I don't need what, how much I don't need, I would say this part I don't have to calculate. This part I don't have to calculate actually. I don't have to calculate this part. This part I don't have to calculate. But I have to calculate one more part that's missing. So this part I am missing there. So if I make a rectangular diagram here, that means it is going to account to this part also, and this part is going to overlap, so this part gets cancelled, and this part is also not overlapping, so final values we can solve. So the final equation can be further simplified. So this final equation can be further simplified in this way, that delta equals to 5/48 PL square. Yeah, actually we can write PL square by 48 EI. After that we write E2 minus 5 E1. E2 minus 5 E1, where your E2 is at the midspan. Your E2 is at the midspan. And E1 is at the ends. Okay. PL square by 48 EI, E2 minus 5 E1. And on similar grounds, we can have a cable that's a bent cable. We can have a bent cable also, having some eccentricity E1, E2 about the neutral axis. There's some eccentricity of E1, and there's some eccentricity of E2 that's above and below the neutral axis. Okay, for that also I would say, we can simplify it again in that same fashion. If this is length of L/2, so this can also be solved in this way, that we have this calculation for E1 plus E2. This is negative, and we have to also calculate the effect because of the rectangle about the neutral axis, and this is some E1. So the moments that gets developed here, I would say this is some moment of P into E1 plus E2 divided by EI, and this is also P times E1 by EI. So these two diagrams we have to calculate about the point A, centroid of those about the point A. Then after that you can get the delta final similarly, and that equation we can write final general equation, that's PL square by 24 EI, E2 minus twice E1. Your E2 value of E2 is at the midspan. So this is our equation, general equation we have. And one more is their final value. If the cable is trapezoidal, if the tendon is trapezoidal, final case is that if the tendon is parabolic, that what we call as tendon is trapezoidal tendon. Okay, let's take that case also. I would say we have this cable. After that it's straight. After that it's also that inclined. So this is our cable. Let's say this is length of L1, and this is also length of L1. This is length of L1. This is length of L1, and this is also length of L1. And if the total length here is twice L2, such that up to the mid part it's L2, and this part is also L2. So for that we have a general equation. For that. And let's say the eccentricity, that is a constant value. Let's say the eccentricity we have, that is equals to E. So your deflection comes to be equals to minus times PE by 6 EI, and twice L1 square plus 6 times L1 L2 plus 3 times L2 square. Now if I say your value of L1 equals to L2 equals to L by 4, if the total length is L, if the total length of the beam is L, such that all the 4 parts are of equal length. So for that I have simplified it. So your equation becomes that delta equals to minus times 11 by 96 P L square E by EI. This is your equation. But we are going to use that general equations of, one is your cable parabolic, one is your cable that's bent, one is your cable that is straight. So these are our general cases we can take. Let's go for the first case. Let's go for the first problem that is related to the calculation of deflection. That's the first part of the problem. First problem related to the deflections. So let's go for that. So your cable is your cross section of the beam. 150 cross 300. So one more part is there. You have this cable, and there's some beam that's 8 meters span. Parabolic cable is there. Parabolic cable, parabolic cable, parabolic cable, and eccentricity E1, E2, eccentricity E1, E2, E2, E1. Cable is parabolic. So your value of E1 is 25. E2 is 75. Okay. And cable is applied, cable has been subjected to that Prestress force of 350 kilonewtons. We are applying that P force equals to 350 kilonewtons. Initial Prestress force of P0. And for the concrete, your EC is equals to 38 kilonewton per millimeter square. And one more thing is there. Calculate the deflection. Calculate the deflection when beam supports its own weight. When beam supports its own weight. So it is actually about the transfer stage. So delta, calculate the delta at the rate of when beam supports only self weight. When beam is supporting self weight. So that means we had to calculate when there was some P, there was some eccentricity of that E, and there was one more part that was self weight. So we had to calculate the sum of these three. What was that final deflection at that case? So I would say, what was the dead load we have? What is the dead load we have? Dead load is actually 24 into 0.3 into 0.15. So that's your dead load, and because of that, your deflection at the midspan is actually downwards. We can write that as positive. That is 5 by 384 omega dead L to the power 4. What is the length? 8. I can write 8 meters. So 8 to the power 4 divided by EI. Your value of E for the concrete, that is 38 kilonewtons per millimeter square, and all the data you have to keep that accordingly, such that you will get a deflection in millimeters. You have to convert all that data in millimeters such that final value is in millimeters. And your value of I for the concrete cross section, BDQ by 12. BDQ by 12. And this part we have to keep in thousands. I would say this is 8,000 power 4 millimeter power 4. And this is dead load. We have to convert it in Newton per millimeters, or we can keep it in kilonewton per millimeters. We can convert that also. And finally your equation would be, yeah, your dead load is actually 1.08. Your dead load is coming to be 1.08 kilonewton per meter. And after that final calculation, your delta because of dead load is coming out to be 4.5 millimeters downwards. Okay. Now one more part is there because of the cable that is parabolic, and we are having E1, E2. We have the standard equation for that. Delta because of P and E, that equation is PL square by 48 EI. And one more thing is there, E2 minus 5 times E1. So we have to just substitute those values. What is the Prestress force we are applying? 350 kilonewton. So 350 kilonewton, I can write it as a Newton. Let's write it as 350 kilonewton into that length of L square. Your length of L square, 8 square, and it's in meters, so I can write 10 to the power 6 millimeter square. This is L square. Then after that, E2 is 75 minus 5 times E1 millimeters. After that, divided by 48 into E, that is 38 kilonewton per millimeter square, into value of I, modulus of elasticity for that. Yeah, moment of inertia, BDQ by 12 millimeter power 4. So final value should be a unit of millimeters. So that final value is coming to be delta because of that P and E, because of that Prestress force. That's 12.7 millimeters, and this is upwards. So we can keep it as negative. So can you tell me what is the net final value when the beam was supporting only dead load? So that is, I would say, this is at the time of transfer stage. This is at the time of transfer stage. That is the delta that has developed. That is 4.5 downwards and minus 12.7 upwards. So negative value of upwards, that means upward value is equals to upward deflection of 8.2 millimeters. So we have at this transfer stage we have 8.2 millimeters of that deflection. Now second part of the problem is going to be started. Second part of the problem. Now it's saying that find the concentrated load, find the point load, concentrated load that we have to apply at midspan, such that we have to restore the midpoint. We have to restore the midpoint to the actual original location, That means to the original support level, That means if there were two supports and beam has gone upwards to some value of delta maximum equals to net value of 8.2 upwards. So we have to restore it back. So how much force should we apply at the midspan such that the final configuration at the midspan is somewhat in this way, so that delta at the mid is equals to 0. So I would say this P is going to have an effect. It's going to do the work such that it would cause the deflection downwards equals to 8.2. Can we say that? So I would say because of the P, we are having that deflection P L cube by 48 EI for the simply support beam, and that should be equals to 8.2 millimeters. What should be that value of P that we have to apply? So that P force would be equals to 8.2 millimeters into 48 into E for the concrete, I for the concrete cross section. So what is the EC we have? 38. Value of EC 38 kilonewton per millimeter square. 38 kilonewton per millimeter square into modulus of that moment of inertia of the cross section, BDQ by 12 millimeter power 4, and divided by that length of L cube. Length is 8 meters, so I would say 8 meter cube and 1000 power 3 millimeter power 3. So your value of P force, what should be the value of P? This is not P force, this is the P external. I would say this is the concentrated load, external load we have to apply at the midspan. This is the service load. I would say this is the service load. So that is coming to be equals to 9.9 kilonewton. Let's take one more problem. Let's take that one more problem we can take. Let's go for that. So we have this beam cross section of dimensions 300 cross 500, and we have two post tension cables. That means the beam is post tension pre-stress concrete beams, and cables we have two number of cables, and each is having area of cable equals to 600 millimeter square. Okay, and initial pre-stress in the cables is 1600 megapascal. 1600 megapascals, and the cable eccentricity of the cable is 100 millimeters. Cable is straight throughout. Length of the total beam is 10 meters. Your modular ratio can be solved as ES by EC, that is 210 gigapascal divided by 38 gigapascal. Okay, modular ratio. And first case of the problem is that neglect. So first part of the problem is that if you neglected the losses, now you need to say what is the delta, what is the deflection value when this beam supports only self weight. That means it's talking about the transfer stage. That means at the transfer stage, at that case we have to calculate delta because of P force, its eccentricity, and because of the dead loads. So this is the first part of the problem. Let's calculate that. For that, I would say we have to say what is the total length of the cable, what is the total beam length, and what is the dead load of the total dead load of the beam. So that would be 25 kilonewton per meter cube into 0.3 into 0.5. That's your 0.6 into 25. That's some 15, I think, 1.5. That's 1.5 into 2.5. That is some 3.6 kilonewton per meter. So this much amount of dead load is there, dead load intensity. Okay, now because of the dead load, can you calculate the deflection for a beam of length L equals to 10 meters? So do you know the equation for that? So you have this beam, you have to say what is the deflection because of the self weight. That's 5 by 384 omega was 3.6 kilonewton per meter, L to the power 4, 10 to the power 3 power 4 millimeter power 4 divided by 5 by 384 EI. Your E for the concrete is 38 into 10 power 3 megapascals into I for the moment of inertia for the cross section, BTQ by 12. Mm power 4. So this is your deflection at the midspan, and this would be downwards positive because of the self weight. This is some value of 3.95 millimeters. 3.95 millimeters. Now if there is okay, this is 3.95 millimeters. Now you have to tell me, because of the eccentricity of the cable, there is some eccentricity of the cable below the neutral axis, 100 millimeters throughout the span, throughout the length of the beam. Let's say in this fashion, such that I would say what is the total deflection that's outwards because of this hogging moment PE, because of this moment P into E, hogging moment P into E. So that deflection because of the, I would say delta because of PE, that's equals to minus times PE L square by ATI, and this value is actually upwards. So that value we have to substitute. Your P force can be solved in this way, that your total force of P naught, initial pre-stress force, would be, we have two cables, each of area at 600 millimeters square, and stress in each of the cables is 1600 megapascals. So that's your initial pre-stress force of 1920 kilonewton. 1920 kilonewton. So I can substitute that value here, 1920 kilonewton into value of eccentricity E. Eccentricity E is equals to 100 millimeters. After that, length of L, that's L square, so that's 100, that's 10 square, and 10 to the power 6 millimeter power 2 meter square, 100 square millimeter square. Okay, after that we have 8 times EI, your E for the concrete, that was given to you 38 gigapascal. 38 into 10 to the power 3, or I can directly write 38 kilonewton per millimeter square into I for the concrete section, BTQ by 12. Okay, millimeter power 4. So your deflection, it's upward deflection, so negative value of delta, that's coming to be equals to 16, how much is that, 20.2 millimeters, 20.2 millimeters upwards. Now for the first part of the problem, it was saying calculate the delta when beam was supporting only self weight, and there was already that P and E also associated with that. So we need to say delta net. In the first case, that is actually upward deflection of how much, 20.2, that's upwards, so we can say this is negative. After that, downwards positive value of, because of the self weight we have 3.95 downwards, 3.95. so final value of deflection is upwards, negative value of how much, 16.3 millimeters. Now second case of the problem, second part of the problem is that if there is at the final stage, if we say that at the final stage there is total loss of, percentage loss of stress is 20%. So we need to say find the final deflection at the midspan, deflection at the midspan, that is the maximum value of final delta, that is maximum. Okay, and for that we have some live load also, live load intensity 18 kilonewton per meter. So we are applying that live load of 18 kilonewton per meter, and I would say equation would be same 5 by 384 L to the power 4 E concrete, I cross section, but only the thing is going to change. That's this UDL. UDL is going to change, so that dead load is going to be replaced by live load. So your deflection, I would say deflection because of live load would be equals to deflection because of live load would be equals to, what was the value because of dead load? That was downwards 3.95. So this was corresponding to what value of dead load? This was for the value of dead load equals to, this was for the dead load of 3.6 kilonewton per meter, but my live load is actually 18 kilonewton per meter. I would say by that concept I would be having some value 3.95 into 18 divided by 3.6, that is 19.75, 19.75 millimeters downwards positive value because of live load, 19.75. So I would write delta because of live load is equals to 19.75 millimeters. And what was the effect because of self weight and net value? This was the net value in the first case, that was transfer, delta transfer net. This was delta transfer net. So we had to take that value also. But one more thing is that whether we have to take this 16.3 or we have this factor of, we have the loss factor also. If you see that there is some loss factor also we had to account. So where this loss is going to be used? In what part of the deflection is going, this part of the loss is going to be used? So I would say for the delta because of PE, we have the equation PEL square by ATI, PEL square by ATI. We calculated that value here, PEL square by ATI, and the value here was 20.2 millimeters. Now I had to multiply that K times, that is 0.8 times the initial value. So your deflection is going to decrease now. Because of this factor now, I would say the deflection here would be K times PE. So your deflection would be now, this part is actually 0.8 of 20.2 millimeters. So this is only, that's 16.16, I think, 20.2 into 0.8, 16.16 millimeters. This is the final deflection, and this is upwards because of the effect of P and E, but for the final stage, this is for the final stage. So let's have the final equation. So final deflection would be solved in this way. So final calculations would be in this way, that your delta at the final stage is because of the delta dead load and delta live load and delta because of PE and K times that. So first case is that because of the dead load, what was the deflection? Because of the dead load, what was the deflection we have? Because of the deflection of dead load, that was 3.95, 3.95 downwards. After that, because of the live load, we have downwards deflection of 19.75, 19.75. After that, we have third effect because of the final transfer stage, K times PE, that was minus times 16.16 upwards, minus 16.16, minus 16.16 millimeters upwards. So the net value would be 7.29 downwards positive. Let me check it. 16.16 minus 19.75 minus 3.95. 7.54. It's coming 7.54. 7.54. So 16.16 is there. 3.95 is there. 19.5. It should be 19.75. Why it's coming 19.5? 19.75. It should be 19.75. 3.95. I think it would be same. Let's keep it as a final value of that 7.54. Let's say this is final value of 7.54. This is 7.54 downwards net value final deflection. So that I think that's the end. Nah, this is the end for the deflections. This is the end for the deflection topic. This was the end for the deflection topic. Now, so one more final topic is there. That is few concepts we have. And after that, this is going to be end of the topic, pre-stress concrete. So the topic here is what we call as transmission length. And this concept is for those beams which are called as pre-tensioned PSC beams, pre-tensioned PSC beams. So what is the case? That you had that anchorage systems, you had those anchorage bulkheads. In that we have fixed that wire. In that we have fixed that wire with some pre-stress force of P0. It was already stressed with some initial pre-stress of P0. After that we are casting that concrete. We have casted that concrete beam. Now we are cutting the, once we cut that, what you call as, once we cut that tendon, what's going to have, we are going to have an effect. We are going to have some effect. We are going to have some effect that we call as Hoyer effect. That we call as Hoyer effect. So what that means, that if there was a cable placed in the concrete, there was a cable placed in the concrete. Now from the side, when you release it, that when you cut this, what you call as wire, there's a tendency of that wire to come back to its original position. And when we are cutting the wire, suddenly there's a chance of that wire to release that energy back, and at that case, at that time t equals to 0, at that time t equals to 0, your tip of the tendon is having stress equals to 0, stress in the end equals to 0. And because of that, at that time t equals to 0 minus, at that time we are having some stress of P0 in the wire, but at time t equals to 0 plus, at that time we are having some stress of 0 in the cable. So, and because of that effect, we say the cable is going to swell near that end. Here the cable is trying to get swelled. Here the cable is going to that kind of swell. So here the cable gets swelled. So there is swelling at the ends. So we cut the cable. At that time your stress at the end is 0. So there is swelling of the cable. And because of the cable is swelling, now there is more contact area here as compared to the initial cable line. And there is development of radial pressure also. There is development of radial pressure also. Radial or lateral pressure is going to develop. There is development of radial pressure, but this radial pressure is going to die down. It's going to die down as we move towards the other side of the length. This lateral pressure is going to decrease, and finally there is a length that finally, after that there is only longitudinal stress. There is only longitudinal compressive stress. So that is only longitudinal compressive stress. So this length that's taken, that we call as transmission length. So I would say in the transmission zone there is lateral pressure also. Lateral or we can say radial pressure is there. Radial pressure has developed in the concrete. Has developed inside this TL. We have that radial pressure. But I want that only direct compressive stress in the concrete, and that should be also only longitudinal. So I would say after TL, after this transmission length, only longitudinal stress is there. Only longitudinal stress is there. Longitudinal stress is there. Okay, so that length, particular length, that's we call as transmission length. There is that what you call as lateral pressure here. Development of that lateral pressure. Okay. So we say that this that transmission length TL, it is a function of that steel. It's a function of that. It's a function of the diameter also. Diameter of the wire. That also it's a function of friction also. So that force is transferred actually by the bond action. If we say that force from the steel, it's going to be transferred by the bond action between the concrete and the between the concrete and the steel. So that bond action here, that bond action is because of one is your adhesion, one is your friction, at that interface, one is your friction, that one more is there, that what you call as shearing resistance. And we also say that one more critical point here is, we say when bond strength when bond stress is equals to 0, at that time TL is going to end. So once we reach to the length of TL, so at this length, your bond stress is going to be equals to 0. So its variation is actually in this way. From the ends, its variation is actually in this way. Your bond stress variation is actually in this way. This is for the length of TL. Finally, it becomes 0. So after that, your only longitudinal stresses are going to develop. And after that, one more concept is there that we call as end zone block. End zone block, or this we also called as anchorage zone. Anchorage zone, and this concept is related to post-tension beams, pre-stress concrete beams. So what this topic is all about, let's say there's some beam, and at the time of when we try to apply that tensile stress on the cable, at that same time there is pre-stressing of those, there is compression of the concrete also. So if there was some sort of that assembly that was trying to apply that tensile stress in the wire, and because of that there is development of compressive stresses at that same time in the concrete also. So that means you are applying that pre-stress force of, let's say the cable is somewhere here. Let's say this is our cable. Okay, this is our cable 1. Let's say this is the cable, and we are applying that pre-stress force. We are trying to apply that pre-stress force in the cable, and because there is some contact area, because of that system, that is anchorage system, or we can say that is system that is a jacking system. Let's call it as jacking system. And because of that, there is a transfer, there is a contact area, there is more contact area, and because of that there is development of lateral pressure, radial pressure, or lateral pressure, that we call as lateral tensile stresses. Lateral tensile stresses get developed in this part, in this region, and that lateral tensile stresses, we call them as bursting tension. We call that part as bursting tension. That's trying to burst the concrete here in this part, bursting tension. So I would say its effect is similar to that of the previous case. So there is development of that radial pressure up to some length that we call as end block zone, end zone block, or anchorage zone. Let's say this is the zone up to which this is happening. And I would say there are some compressive paths. After that, it's the compressive path is straight. There are some compressive paths in this way. There we have some compressive paths, but one more is there. That tensile paths are also there. So finally, if I have that one more diagram that's related to that bursting tension diagram in this zone, so some sort of diagram is formed related to that lateral tensile stresses, and it decreases finally and reaches to the value of 0. So this value is that tensile stresses in this region. That is the lateral tensile stress variation. Variation in the zone of end block. Let's call it as anchorage zone. Let's say this is some L, anchorage zone LAZ. So finally this would become 0 after some time, so that after that there is no lateral tensile stresses. Let's say this is coming to 0 after LAZ. Let's say this length is equals to LAZ. This total length is LAZ, and the maximum value we have, we can say that is corresponding to bursting tension, this one. So resultant of that is causing to try to burst the concrete. Now its direction is that it's a lateral value. It's a lateral direction. It's in the lateral direction. So if you have concrete cross section and you are trying to have a lateral tensile stress, that means there will be cracking in the long direction. So some sort of cracking is going to develop. So that cracking would be horizontal. So we call it as horizontal cracking because of that effect. So this would be some sort of cracking going to develop in the concrete section along the longitudinal direction because of this effect in the post-tension beams. Okay, so to avoid that tensioning, to avoid that cracking, we are going to place some steel bars. We're going to place the steel reinforcement. Let's show that little bit of steel reinforcement. Let's show that there is some steel reinforcement also. Let's say this is some steel reinforcement. steel reinforcement placed in that region to avoid that bursting tension, to avoid that cracking of that concrete in that part. So we are placing that steel reinforcement in this region. This is your what you call as anchorage zone. So for the first case, when we say transmission length, and its value is generally in the range that transmission length is a function of that diameter. So its value is sometimes in the range that 30 times diameter to 100 times diameter. So this is the values for that. Now let's take that final one. So I would say after this end block zone has completed, after that there is only longitudinal stresses. After that there is only longitudinal stresses. There is no lateral stress after that. Only longitudinal stress after that zone. So actually we are trying to apply that horizontal stress in the concrete. We are trying to apply that horizontal stress in the concrete that is longitudinal, but because of this effect there is lateral stress also getting developed. So it takes some length of the beam such that after that, beyond that, there is only lateral longitudinal stresses. So that length that it takes, that we call as anchorage zone for the post-tension beams. Let's have the final topic of the pre-stress, that is called as concordant cable profile. Concordant cable profile. What this means? If we talk about a continuous beam system, let's say there is a continuous beam system. We have number of supports there. There is UDL also, dead load, live load. And can you tell me what is the diagram, bending moment diagram? What is the bending moment diagram? So deflection diagram would be in this way. Deflection diagram is actually in this way. This is the deflection diagram. And if I say what is the bending moment diagram, that would be some diagram would be for the deflection, that for the moment it would be in this way. So this is the BMD for this one. This is the bending moment diagram for these loads. So some moment somewhere at the midspans we have some maximum sagging moment and negative moment at the midspan, negative at the midspan. Similarly, positive here, negative here, positive, negative, positive, and zero at the ends. Okay, this is your BMD. Now, what's the concordant cable profile? Let's say that the beam was in this way, that we had n number of supports. That the beam is continuous, but I want to place the cable now. I would say where should I place the cable from the neutral axis? Let's say this is neutral axis, and where I have to place the cable. Let's say I'm going to place the cable. Let's say I'm going to place the cable as a straight line. Let's say the cable is straight. Can you tell me what's going to happen? If the cable is straight, what is going to happen? So cable is having some force of P, Prestress force, and there is some eccentricity. So your diagram is actually BMD. This is all contributing minus PE for all those sections along the length. Minus PE. Now, if I say because of this one, I want to counteract the effects of external bending moments. So I would say at some locations your negative PE, is, let's say that you had negative PE for entire sections of the length, minus PE. So in this part, you are subtracting some value because we have some value of minus PE here. But in here we have some increase of PE. We have some increase of that minus PE. Here we have some decrease of that PE. Okay, but on the negative side, at the support region, we have increase of that minus PE. So at the support regions, we are increasing the value of PE. So that means there is development of, secondary stresses. We can say there is development of secondary moments. I can say secondary moments. I would say secondary moments. That's minus PE at the supports. Near the supports. I would say near the supports. So near the supports, we are developing some moment of minus PE. So that's an extra moment, that is, we call it as a secondary moment. To avoid that effect, we should place the cable in such a way that these secondary moments are not going to develop. So that profile, for that we call it as concordant cable profile. And the theorem for that, it says that the cable profile, your concordant cable profile is a cable profile. It is a cable profile. Is a cable profile which produces pressure line, Do you know what pressure line is? This is the C line. The resultant of that is the locus of the that C force acting on the section throughout the length of the beam. That is the resultant of that is the locus of C force on the sections along the length. So this is the pressure line. So it says that the concordant cable profile is that particular cable profile which produces pressure line, that is coincident with the cable profile itself. Pressure line coincident with the cable profile itself, So that means that the cable profile should be in the form of BMD. So if I say that BMD is in this way, so I should place the cable profile that is somewhat in this way. That's in the form of deflection. So I have to place the cable somewhat in this way, that this is our cable profile. Let me show that some sort of cable profile should be in this way. This should be some cable profile, and to show that I would say this is your cable profile. That finally I would say the cable profile should be in this way. Let me have it. So I would say in this way the cable profile should be placed in this way. See, at this location near the support we have external negative moment because of external loads. But if I place the cable above the neutral axis, if I say there is some neutral axis also, if I place the cable above the neutral axis, it would cause sagging moment of plus P, so it would overcome the effects of that negative moment. So that's why I'm keeping the cable above the neutral axis at this location where the supports are having external moment of negative hogging moment. So this is I would say this is the cable profile. This should be our concordant cable profile. Oh, so because of that, I would say secondary moments are eliminated. Secondary moments eliminated because of this profile. Okay. And the final codal provision for that prestress concrete is there. IS codal provision. That minimum grade of concrete if you are using that prestress concrete based on pretension, if you are using pretension PSC beams, so for that minimum grade of concrete should be M40. And if you are using post-tension PSC beams, your minimum grade of concrete should be M30. And maximum grade for concrete is that M60. And maximum concrete grade is M60. So we say that for this prestress, when we are finally, I would say finally in the prestress application, in the prestress concrete beams, we are having some steel which is having some permissible stress of some 1000 to 2000 megapascals, 2000 megapascals. But if I talk about RCC, what was the yield stress we are calculating? We said that there's FY 250, 415, 500. So this was the stresses we are allowing in the RCC. But in this case, in the prestress concrete, because the losses, have you seen what was the loss value? The loss value was somewhat 20%, 15%, 25% of the total initial prestress. So if there is more loss, that means we have to make sure that we have a steel which is having more amount of allowable stress. So I would say in the prestress we're having the steel that's whose allowable stress is more, and we are having the concrete that's having some FCK also more, and that's in the range 30 to 40 megapascals. So this is that concrete, because I would say because of the losses, because there are losses in the PSC, so our concrete is also having FCK more, and there is steel also having permissible stress more. So that's your PSC concrete all about. This is all about the PSC concrete. And one more part we can have, that's final topic. So this was your that post tensioning those systems. How do you apply that post tension? For that we have those methods. One was your Magnell-Blayton method. You can see those videos how those machines, how those systems, anchorage systems are applying that prestress. You can check that. You can check that on the YouTube also. So those how to apply those stresses. Magnell-Blayton Freycinet method is also there, and one more is there. Um, Gifford-Udall is there. Okay, and for the pretension, we are saying there is one method that we call as long line method. We can have n number of beams casted together, using the same steel wire. Then after that, we cut the wire at the pre-stressing bed. This is your pre-stressing bed of some length of capital L. There's some bed. Then after that, we cut the wire at those specific locations, and we form n number of beams simultaneously. That's long line method based on the method that is given by Hoyer. So that's we call it as Hoyer long line method for the pretension beams. Hoyer long line method. Okay. So for these we have Magnell-Blayton, Freycinet, Gifford-Udall. Okay, that's all we can have related to that PSC concrete beams. Thank you for watching that prestress concrete.